You have probably seen photos and videos created by AI on social media. Sometimes it's hard to tell whether these images are real or fake. Today's sophisticated text-to-image, text-to-video, or text-to-audio tools like Midjourney, Runway ML, and Suno AI have blurred the lines between real and fake with their advanced technology. But how do these tools do this? It's all thanks to diffusion models. Let's dive into what diffusion models are, how they are made, and what we can create with them. Hello, I'm Vandana Nair, your very own analytics guru. Diffusion models are an incredible technology that brings the natural process of diffusion into the digital world. Diffusion is a physical process where particles spread out slowly over time. In the context of AI, diffusion models take a clear image, considered an ordered state, and gradually add noise to introduce randomness or disorder. This continues until the image becomes completely unrecognizable due to random noise, a process called forward diffusion. The magic of these models lies in their ability to reverse this process. They learn to reverse the process, starting with a noisy image and gradually removing noise to create a new realistic image. This is known as reverse diffusion or backward diffusion. The idea was first proposed in 2015 by Jascha Sohl-Dickstein while he was a postdoc at Stanford. In his paper, Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics, he introduced the core concept of gradually adding noise to data and then learning to reverse that process to generate new samples. However, diffusion models gained widespread attention and usage years later when researchers like Jonathan Ho, Yang Song, and others developed improved techniques. The core of a diffusion model is a probabilistic process called the diffusion probability density function, PDF. It determines the probability of a clean image turning into a noisy version at a specific time step in the diffusion process. During training, these models learn to reverse this diffusion process. This learning happens through different architectures like U-nets and transformers. The first step is to gather a large data set of the type of data you want to generate. For example, if you want to create images of cats, you need to feed the model a data set containing millions of cat images. This data is often sourced from the internet, existing datasets, or through data collection efforts. The dataset must be diverse and representative of the target distribution so the model can learn underlying patterns and generate high-quality samples. The more data available, the better the model will perform. This principle applies to all types of models. Diffusion models can be used to create images in two ways, unconditionally or conditionally. Unconditional image generation means the model directly transforms noise into any random picture. Here we don't tell the model what to create, so it can produce anything. In conditional image generation, we give the model extra information, like text descriptions or class labels, as in CGANs guiding it. This way we can ask the model to create specific types of images. Tools like Midjourney and DALL-E do this. They generate realistic images from text prompts through diffusion models. So how do these images get generated from text descriptions? For this, the models encode the text words into a latent representation or text embedding using a large language model like GPT-4. This text embedding is then input into the diffusion model. The denoising process is guided by the image we described in the text. The model gradually removes noise while keeping the text embedding in mind, ensuring the generated image matches what we described. Diffusion models are experts in creating images, but there are different challenges with audio and video. Video generation models like Sora, Pika Labs, and Runway ML are also based on diffusion models. But the process for video and audio generation differs because it involves sequential data. The model needs to understand the temporal relationships between frames or audio samples. In audio and video, both spatial and temporal information is present, making them more complex than images. In video generation, the diffusion model doesn't work on a single image, but on a sequence of frames. The model starts with just noise for the first frame and then gradually removes noise to create the first frame according to the input prompt or conditioning information. For the next frames, the model uses the previously generated frame as input along with the conditioning information and then creates the next frame by removing noise from the previous one. This process repeats until the entire video is created. The diffusion process for videos and images is similar. but the model must ensure that the time and visuals between frames are correctly constructed to make the video smooth and realistic. But where do video generation models get their data from? Video generation models require a lot of videos to learn patterns and movements. These datasets can come from several sources. Publicly available video datasets such as Kinetics, YouTube 8M, or ActivityNet exist and can be used for training. Like images, online videos can also be used to train models, but careful filtering and curation are crucial to maintain data quality and variety. Now let's talk about audio. Audio diffusion models work slightly differently compared to image diffusion models, but the principle is almost the same. They operate on audio spectrograms instead of pixels. Let me explain how this works. First, the model is trained on a dataset of audio clips or samples. Then the audio is converted into 2D images. This allows the AI model to analyze audio patterns. Then these models use a similar diffusion process to add and remove noise. Finally, the created spectrogram is converted back into an audio waveform using techniques like the Griffin-Lim algorithm. Every coin has two sides. This AI magic is not without challenges. Diffusion models also have limitations. Training them can be computationally expensive because they require a lot of data. Additionally, there are data quality issues, inference time issues, and sometimes these models start generating only limited types of samples, which is called mode collapse. Researchers are continuously working to solve these challenges with some promising approaches. Using recurrent neural networks, RNNs, or transformers for video and audio can better model sequential data. Efficient sampling techniques can reduce inference time. Explainable AI techniques can be used for interpretability. Diffusion models are already being used in many fields, such as content creation, game development, medical imaging, scientific visualization, and product design. These are just a few examples. The generative capabilities of diffusion models will open up many new possibilities. You've seen the magic of Sora. Suno AI is also generating amazing audios. And as research progresses, these models will become more powerful and versatile. I hope this video has given you a good understanding of diffusion models. But if you have any questions, feel free to ask in the comments. And do let me know what you think about this technology. How will it change our world, and what impact could it have on Bollywood or the entire entertainment industry? See you in the next video. Until then, keep learning.